Hello, everyone. Thank you for joining us today. I'm Amy McIntosh, Managing Editor of Stormwater Solutions. Welcome to our webinar, Ensuring Bioretention Media Performance Success, presented by Contech Engineered Solutions. Engineered bioretention media is optimized to filter and/or infiltrate stormwater runoff through a plant-soil microbe complex. Treatment occurs via physical, chemical, and biological removal mechanisms that capture sediment, nutrients, heavy metals, bacteria, oil, grease, and other constituents found in urban runoff. Qualifying and protecting these media components ensures the bioretention media can meet overall performance objectives. This webinar will focus on the framework necessary to transfer raw materials to a blended, commercially installed product. This framework should encompass a standard operating procedures for qualifying, sourcing, verifying, producing, storing, and handling media and media specifications to ensure recipe consistency. We'll get started in a few minutes, but first, a little housekeeping. Participants in today's webinar earn 1 professional development hour. I'll give you directions for receiving your certificate at the end of the webinar. For those of you viewing as a group and wishing to receive a certificate, please download the multiple viewer sign-in form you'll find on the Resources tab of your viewing console. Follow the instructions to receive your certificates. You'll notice on your console you have the ability to ask questions. We encourage questions and will answer them at the end of the webinar based on time availability. Our speaker today is Mindy Hills from Contech Engineered Solutions. Mindy Hills is an R&D project manager at Contech Engineered Solutions and has worked in the stormwater industry for more than 14 years. She is responsible for the technical development and investigation of products for stormwater treatment, as well as ensuring a stringent bioretention media quality control program. Mindy received her Bachelor of Science in Environmental Studies from Randolph-Macon College with a minor in biology. She holds a master's degree in horticulture with a soil science concentration from Virginia Tech. And now I'll hand it over to Mindy.
Thank you very much. Good afternoon, and thanks for taking the time today to learn more about ensuring bioretention media performance success. I want to spend my hour focusing on how to prevent failures of bioretention media. As you know, bioretention systems as a whole can fail for many reasons due to improper design, improper construction, improper installation, but equally important and perhaps less discussed is improper maintenance. The ultimate design goal of bioretention media is to provide a blend that has a porosity that will maintain the desired flow rate with few fines and adequate organic matter to support plant growth and absorb contaminants. Improper media impacts common design criteria that are tailored to meet the design goal, such as storage volume or the infiltration rate of the media. Storage volume is especially important if you're routing the volume through the media. Water quality performance targets aren't necessarily a design criteria, but more of a design goal, since there's an assumption that these performance targets are met if the hydraulic design and media component ratios defined in the design criteria are correct. However, improper media can prevent you from meeting your sediment, nutrient, metals, or other water quality performance targets. But you also have to consider your infiltration rates. If you have poor media that's not providing high pollutant removal due to using unqualified materials, this can also be an issue. So how are our water quality performance targets affected by the use of inadequate media? It means taking a look at the removal mechanisms that support water quality performance. The components of a biofiltration system, they each play their role in removal, but I want to focus specifically on the media today. If media hydraulic capacity is compromised, so much so that you have standing water greater than 48 to 72 hours, you start to impact biological removal processes. Much of the microbial community within the media that supports pollutant transformation and sequestration through aerobic activity will be hindered due to low dissolved oxygen levels. An abundance of biofilm slime can form and further restrict hydraulic capacity and cover absorption sites within the media. Plant roots need oxygen and may suffer in long periods of standing water, preventing the biological process of phytoremediation from even occurring. Physical removal processes such as adsorption and absorption and chemical removal processes such as cation exchange capacity are negatively affected when inadequate media source materials are saturated with high levels of nutrients or metals, so much so that absorptive capacity is compromised and leaching of these contaminants occurs. The media in a bioretention system, it's like an engine in a car. It's what makes it perform. And therefore, engineered media is the heart of bioretention system performance. And so preserving media integrity really is of the utmost importance. A successful bioretention installation involves oversight of media production, not just oversight of on-site construction and installation. Though public domain BMP design manuals will identify generic media specs to avoid sole sourcing, this can lead to gray areas in the specs, making these specifications inadequate. So we need stronger specs and standards for production to ensure the highest probability of success. In the 10 years that I've been manufacturing Filterra media, for example, I've really come to realize the importance of having a documentation framework developed for before, during, and after media production. This framework should provide documentation for transferring base materials to a blended, commercially installed product. A recipe for a successful media certification program involves having specs around not just the blended media, but the base materials to ensure recipe consistency. Standard operating procedures, or SOPs, should be developed around how media is sourced, produced, stored, handled. Additionally, verification testing via QA, QC procedures, both before and after construction, ensures recipe consistency and that the media operates as designed. Bioretention media should be verified post-construction that the media was not compromised during the construction of the bioretention system. And lastly, since media production is a batch process, certification letters should be provided for every media batch produced, ensuring composition, water quality, and hydraulic performance. Historical records should also be filed with information on how each batch was created for future reference. Public domain design manuals, generic media specs, often specify ranges for media composition, including sand, topsoil, and organic matter. Generic blended media specs often include physical and chemical composition specs, as well as permeability requirements. And as I previously mentioned, the design goal of media public domain specs is to provide a mixture that has a porosity that will maintain the desired permeability, but also providing limited soil fines and sufficient organic matter to support plant growth and absorb stormwater contaminants. Common parameters to consider, they include sand, silt, and clay. This can be determined from a particle size distribution analysis. Organic matter can be determined from loss on ignition analysis by burning off the carbon in a muffle furnace. Bulk density is measured based on the dry mass of media in a pre-measured cylinder volume. Available phosphorus and CEC, or also known as cation exchange capacity, are often measured via a weak acid extraction method. Phosphorus can be very labile in soils under saturated phosphorus conditions. Therefore, measuring the soil P-index is important in understanding the leachability of phosphorus. The P-index provides a measure of soil phosphorus content and the risk of that phosphorus moving through the soil. The risk of phosphorus movement through a soil, it can be influenced by several soil physical properties like texture and structure, pore space, pore size, pore distribution, and organic matter. Leachability can be further enhanced with coarse soil texture and increased porosity. CEC is sometimes specified in a media spec as well, just to ensure increased media reactivity for enhanced pollutant absorption. CEC is measuring the amount of cations that a soil can retain, and that includes things like calcium and magnesium and potassium, sodium, hydrogen, and aluminum, and it's found primarily on clay minerals and organic matter surfaces. Media infiltration rates are also often specified, and it's highly dependent upon particle size distribution and media composition. Verification testing should be performed for these requirements via relevant ASTM, USCPA, or other standards. For the sand-based material spec, ASTM C33 is often identified in public domain manuals. However, there are other parameters that should be considered to ensure media performance is adequate. You should ensure the sand's washed, and if it is washed, how much? Ideally, the sand is washed well on a conveyor and it's screened. ASTM C33 does offer a PSD, but the spec provides about a 35% variance on two of the sieves, which would really greatly affect flow rates. Therefore, tighter specs should be considered, or at least a spec that meets your hydraulic criteria. Porosity should be considered as an additional parameter for specs because it affects water holding capacity, flow characteristics, and organic retention. Even particle shape, whether your sand is it rounded or angular or flat, it affects how particles fit together, ultimately affecting porosity and flow characteristics. Two media with the same particle size distribution can operate at two different flow rates due to the differences in particle shape. Moisture affects component blending ratios, so you could end up with a higher organic content than intended because your sand was saturated. Chemical composition provides macro and micro plant available nutrients that are also leachable. If you're receiving quarry sands from an area heavy in limestone, this could significantly raise your pH and affect plant health, effluent pH, as well as removal efficiency for pH-dependent reactions. Organic-based material specs usually identify compost. However, some specs just state compost, while others reference the U.S. Composting Council, with the latter being appropriate for a spec. The U.S. Composting Council has specific criteria around manufacturing compost to ensure a more consistent product. The U.S. Composting Council helped develop TMEC. It's known as the Technical Methods for the Examination of Composting and Compost, to provide, it's a science-based manual of rigorous test methods specifically appropriate to compost. Additional parameters for developing an organic spec, they should include identifying the feedstock. Is it plant-based or food-based or other based? What's the method of composting? Ensuring the compost reaches the right temperature and is turned appropriately will affect maturity. Maturity rates are based on oxygen consumption and CO2 generation. If the compost isn't adequately matured, you could have more leaching of nutrients and less pollutant removal. Organic content and your carbon to nitrogen ratio are also affected by maturity. What is your particle size distribution? A loamy sand, sandy loam, or loam topsoil generally don't have PSD specifications, and it can be highly variable depending on your source. As a result, the media can have higher than desired fines, which can result in lower than desired infiltration rates. Is the compost or topsoil screened to eliminate trash and debris? pH shouldn't be too acidic or basic so as to not affect plant health or removal performance. Consider a leachate analysis as well to ensure high concentrations of nutrients and heavy metals aren't leaching from the organics. An attrition test would provide information on how long the organic matter would perform. Several years back, actually, both Herrera Environmental Consultants and Washington State University identified pollutant leaching, some of it long-term, from Bioretention media in the city of Redmond, Washington. It was largely the result of the compost content with high leaching of nutrients and copper. Herrera reported about 19 different bioretention soil mixes tested. With all 19, the 60% sand and 40% compost mix was the worst performer in terms of pollutant flushing and pollutant reduction. Like most bioretention media specifiers, compost is used because it offers all these great benefits. It's a local waste product. It grows plants well. It has great water holding capacity and high cation exchange capacity. But these benefits were really counterbalanced by initial and sometimes long-term flushing of the nitrates, phosphates, and dissolved copper. Listed in this table are various organic content requirements for bioretention specifications around the country. You'll see there's quite the discrepancy in some of these specs, both measured as a unit by weight and by volume. For example, Western Washington requires 5 to 8% organic content by weight, while Maryland only requires 1.5 to 4% by weight. So the Maryland minimum organic content, it's over 3 times less than that of Washington. Virginia requires 3 to 5% organic content by volume. North Carolina 5 to 10. Texas Edward Aquifer 20 to 30%. And the rest between 30 and 40%. So we seem to be all over the board here, between 3% and 40% by volume. These disparities ultimately lead to inconsistent performance if you're targeting the same performance standard, especially flow rate. And then you mix in an unqualified compost at 40%, and the amount of nutrient leaching could be quite excessive. I'm not saying that 3% is better than 40 or vice versa, since performance standards may be different in different areas to support different pollutants of concern or maintenance frequency or different climates, but that performance monitoring needs to support these standards so that we're using consistent and justifiable standards. The EPA regulates land application of waste materials and substances containing heavy metals. The EPA's Code of Federal Registry, Part 503, discusses the final use or disposal of sewage sludge, as generated from treatment of domestic sewage. That includes standards for sewage sludge that's applied to the land, also known as biosolids. The technical methods for the examination of composting and compost references this code for land application of biosolids to serve as a guide for compost for the maximum application thresholds for heavy metals concentration. The concentration of each metal in the material is not to exceed the average monthly concentrations listed in this table. In reviewing these numbers, I have particular concern, especially with copper and zinc. Just to give an example, copper is at 1,500 milligrams per kilogram. That seems quite high. For land application where appropriate precautions are taken to blend the biosolids into the soil to prevent loss from runoff, this may be less of an issue. However, in a stormwater treatment system, these levels of metals seem high. You could blend in at 5%, that would still give you about 75 ppm. So that is still somewhat high, especially when crop-producing soils on average are around 30 ppm. The availability of copper in the media can be dictated by many environmental factors like pH and redox potential, equilibrium reactions. If the media absorption sites are already saturated with heavy metals, how can we capture much more heavy metals in the stormwater as the biofiltration systems are actually intended to do? Additionally, too much organic matter can contribute to increased leaching of dissolved organic carbon as it breaks down, and this can lead to leaching of heavy metals bound to dissolved organic carbon through organic complexing. This is an example of a public domain blended media spec that I pulled from Virginia. I use Virginia only as an example since that's where I'm from. This table is taken from Virginia DEQ's Bioretention spec, providing more specific information on the sand, topsoil, and organic matter content. I have both the current and newer draft standards for comparison because I want to focus on the spec for phosphorus. Phosphorus fertility requirements, they're sometimes listed in bioretention specs to ensure there's enough phosphorus in the soils to support plant growth. However, you have to be careful not to have too much phosphorus as you end up with a soil that's saturated in phosphorus and it begins to leach. The potting mix soil that's planted with a plant, it provides nutrients to help support growth during the establishment period. The stormwater itself is a great food source for the plants long-term through the introduction of phosphorus from various sources like fertilizers and birds and pet feces, leaf and grass degradation, all providing quite a bit of phosphorus loading to the plant. The appropriate available phosphorus should be between 7 and 21 milligrams per kilogram per the 2011 standard that references the Virginia's 2005 nutrient management criteria, which corresponds with the fertility rating from minus medium to minus high. That standard has since been adjusted in 2013 to low to medium for 5 to 15 milligrams per kilogram. These levels are appropriate enough for plant establishment without causing environmental concerns, but would really be low for agronomic soils. The big point I want to make between these two standards is that the newer standard is now including two different phosphorus ranges depending on the method used. Soil testing labs can vary in the chemical methods they use to assess soil nutrient levels and the manner in which they actually report the data. A lot of mid-Atlantic states use the Malic 1 extractant phosphorus analysis method. Other labs use newer Malic 3 methods. Some labs report the results in parts per million, some in pounds per acre, others as a predictive index. Virginia's newest guidance actually states both acceptable phosphorus value ranges for the various methods. As shown in that upper right corner of the slide, you can see there's quite a difference showing the 5 to 15 milligrams per kilogram under Malic 1 and the 18 to 40 milligrams per kilogram under Malic 3. Some state guidelines may not list the analysis method, so we just need to be sure what analysis method we're using. Very simply, different procedures usually extract different amounts of nutrients from the soil, but if properly calibrated, they can provide valid results. Again, the Virginia Nutrient Management Handbook does provide calculations for converting phosphorus values among the various methods, so you can properly convert your values to match that of the state guidelines. The nutrient management values provided in the table are based on Malic 1 per the Nutrient Management Handbook. So any lab providing Malic 3 or other method would have to be converted to Malic 1 to evaluate your results against the state phosphorus bioretention guidelines. We need to rely less on nutrient ratings since these are based on agronomic fertility requirements and look more at the actual values and ensuring the methods are synonymous for the lab and the state guidelines. Soil testing, it's an important agronomic tool for determining crop nutrient needs. It evaluates the fertility of the soil to determine the basic amounts of fertilizer and lime to apply. But bioretention soils aren't crop yielding, they don't produce crop yielding plants. What's good for agronomic growth is not always good for the environment. So we just need to be careful about how we apply the criteria. In the past, engineers and government agencies have used lab ratings for bioretention media, like I've listed here, from very low to very high. But we need to think about our application, and the values are really more critical than the actual nutrient ratings. I've taken a few excerpts from Virginia's Nutrient Management Handbook describing what the low to high categories mean and how they're derived. The figure on the right illustrates a typical plant response curve based on percent yield as influenced by varying levels of soil nutrients. With a low to medium category, as shown in the previous slide, this fits the plant's response curve for ensuring crop or turf grass yields, requiring that a portion of the nutrient requirement come from fertilizer. This may be applicable, like I said, to crops and turf grass, but for landscape plants in the stormwater treatment system, fertilization isn't really needed unless you're falling in that very low range. Like I said, plants in a bioretention system are getting nutrients initially from the potting soil and from the runoff as a form of fertilizer long term. The hydraulic performance blended media spec usually contains a permeability spec containing minimum permeability in inches per hour. This is typically between 1 and 5. However, oftentimes the test method isn't identified. This can make a huge difference in what volume the media actually treats. Infiltration rates are affected by head development on the media, as well as media depth and various physical characteristics like soil structure, compaction and bulk density, organic matter, moisture content. Therefore, hydraulic conductivity is a more accurate unit of measure, and that's what's required actually by the Washington State Department of Ecology. And Darcy's Law depicts this relationship. Infiltration rates, or initial rates of infiltration into dry surface soils, can be quite rapid. It's what's called a wetting front, and then they'll decrease as the soil wets and begins to swell, and it's pictured in this graph depicting what's called the green ant relationship. Assuming constant head conditions, the infiltration rate will equilibrate, and it reach an asymptote after some period of time to approach and reflect the internal permeability of the underlying media itself if it's designed with an underdrain system. So why does bioretention media not flow as designed? When specifically looking at the media, oftentimes it's the organics that are too high, the particle size distribution too fine, too much silt or clay, contamination in the base materials or blended media, the media wasn't homogeneously blended, or the media is blended with saturated organics. Saturated organic material can actually throw off your blend ratios, as well as cause the media not to be homogeneously mixed. Hydraulic performance, it's just as important of a performance target as water quality performance. Many bioretention systems are volume-based and store the water quality volume above the media surface. If you decide to reduce that volume by defining the volume as the pore volume in the media plus stored above the media, then the infiltration rate in the media becomes more important because you need to route the runoff hydrograph to avoid quickly filling and overflowing the system. So the volume above the media is smaller, and volume control is achieved by subsurface infiltration of the treated water. But if your media doesn't flow as designed, your system's no longer able to capture and treat the peak flows. So ensuring your media is within spec can help ensure you're still treating your water quality design storm. Now moving away from media specs and into SOPs. A framework for media documentation should encompass SOPs utilizing strict verification testing for sourcing, qualifying, producing, verifying, storing, and handling media. SOPs are internally developed procedures tailored specifically to managing bioretention media from its inception to installation, as well as ASTM, EPA, or other approved test methods for verification testing of composition, hydraulic capacity, and quality performance. SOPs aren't just specific to media suppliers, but those providing base materials, those purchasing media for resale, or contractors blending or storing media on site. Bioretention media suppliers should follow SOPs dictating how to properly source and qualify new components to make certain the final media product performs per the design specs. Consider where the base materials are sourced. Issues such as leachable nutrients, metals, organics, or even toxicity characteristics can be identified. Quarry sands mined from land historically used for agriculture or from an EPA brownfield site or an inappropriate feedstock compost source can lead to potential leaching. Fertility testing can properly qualify source materials, as previously mentioned. Finding an available, uniform, and consistent source allows for less variability in the final product and ensures alignment with the product specs. If any of the media components are of limited supply, requalification efforts can be time-consuming and expensive and result in using an alternative source not previously qualified due to project time constraints. This could result in design flaws if the media significantly deviates from the original spec. And then lastly, consider location of base materials, as transportation costs can increase pricing depending on location. A production SOP should describe the components and tools necessary to manufacture media to meet the spec. If media is blended on a project-specific basis by the contractor, especially in situ, a production SOP describing the process for bioretention media manufacturing is crucial to guaranteeing the media or components are procured from approved suppliers and that proper equipment and components are utilized. This should be a process providing directives on pre-qualification of suppliers, contact information, equipment settings, specific components, ratio of components, and reference specs and testing SOPs accordingly. Difference in source materials, operators, and blending equipment, they can cause variations in the production method. So an SOP should really be written so that two different people following the manual will produce a bioretention media batch that both meet the same media spec. Therefore, a production SOP alone will not always result in the same outcome, and media specs become a critical part of the framework for media recipe consistency and need to be referenced in the SOP. The critical parts of a production SOP include pre-qualification, coordination, calibration, blending, and post-QA testing. Pre-qualification includes sourcing appropriate base materials per the sourcing SOP and conducting base material and blend verification testing to qualify sources and confirm lab blend meets the performance specs. Scheduling a media blend requires quite a bit of coordination. The appropriate equipment must be identified for blending. You need to have a blender and operator that are willing to be precise, and they can allot the time to recorrect if the blend's outside spec. You should be on site when base materials are delivered to prevent material contamination and ensure proper storage until the actual day of blending. On the day of blending, time has to be allotted for equipment calibration. You want to start off slow during initial blending for calibration and just run a small calibration batch because you'll likely have to reblend it to correct the pile. If you're using a mobile blending operation, equipment settings can change as equipment pieces are jostled around during transit. Ensure hoppers, gate openings, belt speeds, that they're all correct. If you're bucket blending, are you blending by volume or are you blending by weight? And if it's by weight, you'll need to have a scale accessible for weighing buckets for calibration. For blending, you use your base material ratios that were predetermined during pre-qualification lab testing. QA testing must be performed on the calibration pile to ensure the final product is within spec and that base material ratios are correct. Post-QA testing should follow blending to ensure the final product meets all original pre-qualification specs. There are what I call uncontrollable issues with blending that can affect field performance that you should be mindful of. The weather can significantly affect whether your blend meets spec. Freezing temperatures in winter can make for poor blending conditions when the moisture in the sand or organics has caused the material to freeze together and can't go into the blender. A frozen surface crust will actually form in the piles of stored material. I don't recommend blending in the rain. Rain can saturate organic material and throw off your blend ratios, as well as cause the media to not be homogeneously mixed. Additionally, organic material can smear when it's really wet, losing its structural integrity, and this can affect hydraulic performance. Opposite of being too wet, media that's being too dry. And if you're blending in a very dry climate, that can prevent media from being homogeneously blended. As previously mentioned, the media must maintain some moisture so that the organic material will coat the sand and not fall out of it. Equipment failures, while not directly impacting media performance, can affect project timelines. and people may be more pressed to cut corners when they're running behind. Equipment can and will break down, and so there needs to be contingency in your blending schedule for this occurrence. Media is sometimes installed using a conveyor when shipped to site, but throwing material off at a fast rate and a good distance will throw off your particle size distribution, since the lighter material actually falls out sooner than the heavier material. So you end up with this horizontal stratification across your media bed. So limits need to be set for how far you can actually sling your media into an excavated area. Lastly, operator error can occur. And again, it's just allowing for that time contingency in your project schedule to correct the media batch. That's why it's good to buy from a supplier that's experienced with these issues versus trying to control contractor blending on site and you don't know the conditions of the site. Storage SOPs are just as critical as media production SOPs. If bioretention media is to be stored before use, especially if it's being stored on site before installation, an SOP should be provided to contractors or other purchasers on how to properly store media. Issues with storage can include cross-contamination from other stored materials, as well as tainted water and debris mixing in with the media. These types of storage issues can be prevented by bagging or tarping media, placing media on a concrete pad, or placing the media on similar bedding material and placing the media in a bin with walls. The picture here illustrates a really great job of media storage with the media placed on a concrete pad and tarped. If you're purchasing media, ask the supplier for a tour to ensure proper media storage. This photo illustrates improper storage. There should be separation between bioretention media and any other media. Here you see the underdrain and media are stored next to each other, and the media is actually overflowing into other material on the other side. In addition, tainted water and debris should be kept away from the media to prevent contamination, and silt socks are recommended for use where this is an issue. Sampling, it's equally as important as testing, and the sampler should use every precaution to obtain samples that will show the nature and condition of the materials which they represent. What a waste to test media or aggregate that's not representative of what's actually going to be going into your biofiltration installation. If media or base material is stored as a stockpile, samples should be collected by the supplier periodically, following a proper sampling SOP that references appropriate ASTMs and samples tested to ensure media is within spec. ASTM D75 and AASHTO T2 are really great examples of how to properly sample aggregate. It distinguishes if you're sampling from a stream flow, a conveyor, a stockpile, some sort of transportation unit. But there are a few notable requirements of these protocols if you're sampling a stockpile. First, you want to sample at different heights on the stockpile. And this is due to the fact that as aggregate's thrown off the conveyor, the coarse part of the gradation's falling to the outside base of the pile. You also want to create a smaller, separate pile using power equipment like a skid steer, just to allow for a more homogeneous PSD. Also, you want to collect samples from the area of the stockpile representing material that's currently being shipped. And then the surface of the stockpile shouldn't be sampled if you're collecting material directly from the stockpile without creating a separate pile, as the surface is affected by weathering, and that can cause the smaller fines or organics to actually be pushed further into the stockpile. And you can see the illustration here in that far right corner, just showing the biofiltration media stockpile and how the organic material is actually pushed inwards a few inches due to weathering. Additionally, each new media batch produced should receive a batch number just for tracking purposes. And you should reference samples. These should be inventoried should there be any future issues requiring further testing. Media should maintain some moisture, like I've said, just to prevent segregation of components and ensure a homogeneous blend during storage and transport. This figure demonstrates visual differences in the same mass of media under different moisture conditions, actually contributing to differences in volume. The media is more porous and fluffy, so to speak, when it's wetted, and the decreased porosity with the dry media can result in reduced flow. Media transport has its own set of issues as well. Trucks hauling bulk media should be cleaned prior to use just to prevent contamination from remaining residue from previous loads, and loads should also be covered. Verification testing should cover before, during, and after media production, as well as post-construction. I said that specs should be performance-driven, but how do we actually verify performance? I've defined QA and QC here, quality assurance and quality control. Just so that you understand, there needs to be just as much oversight into blending the media as there is in ensuring consistency throughout the use of the media stockpile. QA is process-oriented, ensures the development process is adequate to ensure objectives are met, and improves production to prevent issues later on. Equipment calibration before blending would be an example of a quality assurance. QC is product-oriented, and it's designed to evaluate a developed media batch to reveal product defects. A media supplier collecting a quarterly sample from a media stockpile for verification testing would be an example of a quality control process. So why do we need QA/QC? Media outside spec can be identified, and further QA/QC investigative procedures implemented to identify the issue as media production, storage, or other media process. Bioretention media is comprised from natural products, and these exhibit natural variation, thereby requiring more QA/QC than maybe a more consistent or synthetic product may require. Media production is a batch process, like I said, so testing should occur with each batch. Different methods of blending can be used by different suppliers, leading to a different final product. Various QA tests should be conducted to ensure the blending equipment is effective or that it's properly calibrated to meet the media spec. And directions can get lost in translation, and therefore being on site for new suppliers really is necessary. Blending operators need clear guidance like, is it by weight or is it by volume that we're blending? No blender we've ever met has had to meet the level of QC we require. Media substitutions are sometimes made due to project deadlines or simply because contractors often don't understand the technical nature of the product and they haven't been properly trained, and so sometimes incorrect material can be delivered to a job site. And media is the performance driver, like I said, so shouldn't we ensure its performance? And lastly, suppliers of biofiltration media can use these stringent tests and as a marketing tool. They can say, I've verified X performance via X test methods. There needs to be more emphasis on source qualification. Verification testing alleviates many of the issues observed with public domain bioretention systems. Tests should follow approved testing methodologies where possible, just to provide equal evaluation among different media. Excessive nutrient leaching, like I said, due to high p-index materials, or metals leaching due to unqualified compost can occur without proper testing to evaluate the composition of materials in a bioretention blend. Manufacturing QA tests to consider for qualification might include PSD and moisture, organic content, hydraulic testing, and water quality testing. Some others might include that you might want to consider are bulk density, porosity, particle shape, silt and clay content, pH, cation exchange capacity, fertility, soluble salts, leachate tests, even microscopy or toxicity. You don't hear toxicity typically mentioned with stormwater treatment testing, and there's really few published studies on stormwater media toxicity testing, but unknowingly adding toxins to receiving waters we're trying to clean up, it seems somewhat counterproductive. So especially when you start looking at adding amendments into the media side, I think regulatory agencies should consider requiring toxicity testing of initial leachate of all biofiltration media. Hydraulic verification testing should also be performed to ensure the permeability criteria is met. Just as an example, each new Filterra media batch receives hydraulic column tests during blending to ensure the design flow rates being met. Quarterly hydraulic testing is conducted thereafter as the stockpiles being used to verify flow. Hydraulic conductivity is measured rather than just infiltration rate because it's a more conservative approach to flow rate measurement. There are standard methods for conducting permeability testing on slow flow media. However, a standard method doesn't exist for high flow rate bioretention media. Therefore, third-party consultation was sought to develop a suitable flow testing protocol that could be implemented in both the lab and the field. This test method, it was conservatively developed to test the media under both dry and saturated conditions, as well as to obtain 3 methods of hydraulic conductivity, including we look at rising, constant, and falling head. And basically research and development just ensures these flow rates are synonymous before moving forward with verifying a blend. Pilot scale, you can see pictured here on the left. It's the same configuration as a full-scale Filterra system. It's about 15 times the filter surface area of a column test to ensure flow rate can be duplicated in the Filterra box configuration, and there's less chance for edge effects. This is an example illustration of a hydraulic capacity SOP developed by Contact R&D. Lab-scale hydraulic testing is performed in columns just to represent the same depth of components in the system in the field. Post-construction verification is highly recommended to confirm hydraulic capacity was not compromised during construction. In situ flow rate verification should be conducted at several locations across the bioretention media surface area. For slow flow bioretention media, double ring infiltrometers will often suffice. High flow bioretention media requires a larger testing apparatus to enable a greater volume of water to be introduced to capture higher flow rates. What we've essentially done is modify the lab columns for field testing, which is backed by thousands of tests. Using lab-based initial verification testing to confirm the media meets specification over time is not ideal because the media it's an ever-changing material, much controlled by the biological community and physical and chemical processes that occur both during and between storm events. This is not just a maturation process, it's an evolving change in properties over the lifetime of the media as the rhizosphere becomes a more habitable place for the microbial community. The media ages like a fine wine. It's with performance only looking better with age. The media sample collected in year 10, it's not going to look like the media sample installed at year 1. Yet specs are often only written to confirm media installation. And once they're installed, the media oftentimes is forgotten about. One of the biggest variables is organic content. Organic matter in the biofiltration system, it tends to increase over time as organics are introduced to the system through runoff containing organic debris, as well as leaves, stems, roots from the plants themselves contained in the system. Additionally, mulch degradation over time contributes organic fines to the media bed, replenishing the system's organics as they're consumed by microorganisms, especially if you're not actually replacing the mulch, but simply adding more mulch over time. We've collected media samples from high-flow bioretention systems of different ages and observed an increase in organic content over time. You might think, well, my flow rate's going to be reduced with this increase in organic content, and this certainly hasn't been something we've observed in studying older systems, and this is likely due to the fact there's processes benefiting hydraulic capacity that counteract this increase in organic content, like physical processes like wetting and drying of the media that creates preferential flow paths over time. You have shrinking and swelling of the root system during wetting and drying cycles, as well as root penetration, and root die-off that creates microchannels. And additionally, plant roots and associated microbiological growth, they provide exudates which build and maintain soil structure, and this increases macropore development for maintaining infiltration rates. So how do we test this dynamic environment? You have a system failure. What tests are going to employ to determine whether the media performance has suffered or if there's another site issue? And I think you got to look past this specific organic content or specific PSD or whatever the criteria in the spec is, and really focus on your end goals, those being water quality performance and hydraulic performance. If you've proven through your initial verification test at installation that your base and your blend materials are qualified, then you should be meeting your water quality performance targets. And therefore, the real focus should be on hydraulic performance, which could be quantified through infiltrometer testing, as previously mentioned. However, these tests can be cumbersome from a time standpoint, so perhaps a simpler standardized method needs to be developed for field application. And certainly a plant serve as a second good health indicator. Historical records should be kept by the supplier for every media batch produced. Batch historical records should include assigning batch numbers for easy reference, recording component ratios, recording batch dates, because you track usage rates so that you allow yourself enough lead time for verifying the next batch. Record equipment settings for each batch, record verification test results, and production cost per batch. Media batch letters should accompany each shipment provided by the supplier to provide assurance to the customer the batch has been properly verified, and it should include a reference number to know the certification is relevant to the current inventory so the letter isn't out of date. If the media is being provided to meet a design manual spec, the certificate should reference requirements in that media spec. So in conclusion, consistent media specs are needed for the same performance targets. With consistency among specs, we can't guarantee, or without consistency among specs, we really can't guarantee media water quality or hydraulic performance. We need documented and uniform SOPs to properly test and evaluate media as it's transferred from a raw material to a blended commercially installed product. And let's remember, it all starts with the base materials. Our media producers must have proper QA/QC procedures to ensure proper base materials, blending, and storage. And even if we have the proper testing and documentation to guarantee performance and installation, how do we know the performance over time? We need standardized methods for evaluating media condition as the media ages and to determine maintenance frequency. And following the appropriate media specs, SOPs, QA/QC procedures, the stormwater designer can really be confident that the use of their media in their plans is going to yield the same performance as specified in the design manual. And yes, the media will cost more. You can't expect to have this level of quality and detail surrounding media qualification without an increase in cost. While you may pay more upfront, you'll be paying less over time versus installing an improper media and having to replace it in a year's time. Lastly, where do we go from here? I've listed several avenues for consideration. I think establishing a media task committee, potentially within EWRI, perhaps through their Urban Water Resources Research Council or with WEF as part of their stormwater committee would be a good start if we can bring the right stakeholders to the table. We can start driving test procedures through the ASTM process for inclusion into ASTE EWR publications and webinars. Regulatory agencies can establish a list of approved suppliers based on the type of bioretention media criteria I've outlined. Ultimately, suppliers, producers, designers, regulators, purchasers, they all need to begin holding each other accountable by asking questions pertaining to the information that I've presented here today. So I'll end with another lesson learned. You'll end up with boulders, or as the Flintstones would have it, bioretention in the town of Bedrock, if the bagged media is not tarped or stored in a temperature-controlled environment during wet winter months. So write and follow those storage SOPs. And with that, I'll open up the rest of our time to questions.
Thanks so much, Mindy. Okay, it looks like we have a couple questions here. The first one, are any of your media regenerable? And if so, are there separate SOPs, QA, QC for the regenerated materials?
So with bioretention media, we really see it as being very sustainable and not needing to be pulled out and regenerated. As long as bioretention media, as long as it's receiving proper maintenance, it really should last indefinitely. The systems become more sustainable as they age. Your absorption sites increase just through the introduction of more organic matter and through the extension of your plant roots as they grow. You're increasing your biomass, so you're increasing your phytoremediation capacity. Now, in a high-loading site, you could exceed the capacity of the system, and at that point, we would certainly want to look at the media and perhaps recommend replacement.
Okay, next question. A bioretention media has considerably higher infiltration rate than what is used in designs. Any suggestions as to why that is?
I'm guessing the question's asking regarding medias that do have higher infiltration rates. I guess if you see it in the field and you're wondering why is it faster than what's in the design manual, I'm guessing that's what the question is targeting. I would say, or if you're using a media that has a higher infiltration rate than what's in the design manual, I'm not sure exactly the focus of the question, but I'll answer it. I can answer it in different ways. But if you're testing a media and it's operating higher in the field than what's in the design manual, that's not a bad thing. These flow rates increase over time. We see this maturation period. Like I said, you have the shrinking and the swelling of the soils and the organic matter, and that's, like I said, creating this preferential flow rates. The roots, as they expand and they die off and grow, you're going to see these infiltration rates increase over time. So I don't think that that's going to negatively impact performance. That's certainly not something we've observed in our own studies. So I hope that it addresses the question.
Okay. You mentioned an ASTM standard on slide, they say 22 or 23, regarding storage, transport, or sampling. But the person asking the question didn't get the number. Can you go over that standard again?
Yes. So that is ASTM D75-97. And there is a comparable standard. It's called AASHTO T2. T as in Tom and the number 2. And they, like I said, they're really great examples for how to sample aggregates in different methods for stream flows or stockpiles or conveyors or transportation units.
Great. Next question. This question says, please speak again to mulch. We clean out all decayed mulch to the medial layer when doing annual or twice annual maintenance. Is there enough decay during that time period for organics to make their way into the soil?
Yes. Yes. We recommend, depending on climates, anywhere from 6 months to a year to remove that mulch. And certainly we've seen the mulch is going to, it's definitely going to stay intact. You'll see some degradation, but it's not enough to impact flow rates. We do see, like I said, we've actually gone out and sampled media over time and looked at organic content. And we've seen that organic content increase over time. And that's not just from the mulch. That's also from the plant itself, from organic material and the stormwater runoff that's contributing carbon to the system. And especially as these microbes in the system are taking that carbon, taking the mulch and breaking it down. And like I said, it's replenishing absorption sites in the media long term.
Have you seen data correlating long-term performance media to the design specs?
I have for Filterra media. I can't speak as much to public domain systems. And we've actually conducted long-term performance monitoring now over 10 years on some of our systems. And we go out, we try to go out quarterly, and we have third parties sample the systems. And we want to make sure that we're meeting our performance claims, and we want to know over time, what is this media doing? And so we're seeing we're meeting our sediment removal efficiencies, we're meeting our phosphorus removal efficiencies, we're meeting our metals, when a system's 10 years old. And like I said, it really does get better with age. You kind of have that initial flushing when it's first put in, and then these systems just over time do better as like I said, you're increasing that plant biomass, you're increasing that microbial community in your rhizosphere that all contribute to helping with removal performance long term.
Are there any specific suggestions for media design in colder climates where frost penetration is deeper?
I would say that, certainly if you're installing media, to try to not do it in the very coldest time of the year, because I kind of went over some of those weather issues that we can have. But in terms of frost penetration, that's not something we've really observed, especially in systems that are contained in a box. Usually that just, it insulates the media to where we've not seen that. But even in some of our systems like the Bioscape system, that's not something we observe where cold climate really shows an issue.
Okay, next question. Is there a maximum clay percentage above which the infiltration rate will dive?
You really want to keep it depends on what your infiltration rate design target is. I would suggest, if you're shooting for something really low flow, like an inch per hour, you'd probably be with 5% and below would be fine. But if you're shooting for something higher, I would certainly start targeting more like just a couple percentages, maybe even 1%. Clays are, they have a high swell capacity, and it just takes a little bit to greatly throw off those infiltration rates.
Can the media become saturated if, for example, an unplanned source of nutrients is introduced into the watershed? Would replacement or redesign be necessary?
It's really going to be site dependent and dependent upon that pollutant loading, how long it lasted, did we kill the plant? Was it a one-time incident? So there's a lot of questions around that question, but at some point, and under certain conditions, of course the media can become saturated. If you have a spill of some sort, or you've got a lot of heavy metals or oils or something coming in off the watershed, you would really have to go in and see how is the plant doing. You could go in and actually take media samples. That's what I would do. I would send them off for fertility. Look at your nutrients, look at your metals, or whatever that pollutant of concern is that you're concerned may have saturated the media, and determine whether or not it's at levels that are appropriate for the plant. And certainly you could do some monitoring of your effluent to see, well, is that spill or what happened is that sort of beginning to equilibrate in the system, and the system's starting to actually replenish itself. I mean, like I said, they are sustainable. There is, they can come back, but obviously there's a limit to everything. So like I said, I think it's somewhat site-specific.
Okay, great. And then how do these mixes withstand the hot and dry conditions of Arizona?
So with really dry climates, you have to really look at a different specification. I think it's not just the specification of the media, it's also the plants. You want to look at plants, these xeric plants that really like dry climates that can or that are really drought tolerant. In terms of the media itself, I would look at increasing organic content just to help maintain moisture in the system. You need moisture for any of these biological reactions to occur. It's not just supporting the plant growth, but it's supporting that microbial community. And it's helping keeping the mix, especially if you're installing it. You want to make sure there's moisture in that mix. You have to be really careful with these dry climates because material can dry out, especially if they're stored in super sacks. So we have really stringent criteria around our moisture contents to make sure that this doesn't happen. And certainly I would recommend irrigation if possible.
Okay, great. Thanks so much, Mindy. So that was our last question. So that wraps up our questions and the webinar. Any questions that come in that we might not get to will be answered offline. And a PDF of this presentation is available in the Resource tab. Please stay logged in after you hear the webinar end to receive the PDH certificate. You will be linked to a form with spaces for your name and email address. Fill out the form with your name as you'd like it to appear on your certificate. The email entered should be the one with which you registered. The complete certificate will appear on your screen. Print for your records. For those viewing as a group, we hope you've downloaded the multiple viewer sign-in form from the Resources tab of your viewing console. Please follow the instructions to receive your certificates. Please also take a few moments to answer the exit survey that will appear on your screen. Your response is greatly appreciated. Please also stay logged in after answering the questions, and you will be redirected to receive your PDH certificate. And the first question of the survey, are you interested in any on-site stormwater presentations from contact for you and your team? If yes, what topic? Number 2, do you have any immediate projects that require a stormwater management solution that we may provide you with technical support? If yes, please explain. And finally, would you like to sign up for Contact's monthly e-newsletter to read case studies on how other engineers have solved stormwater and other site challenges? And again, after answering these questions, please stay logged in and you will be redirected to receive your PDH certificate. On behalf of Stormwater Solutions and Contact Engineered Solutions, I would like to thank everyone for their participation. This webinar will be archived within 48 hours, available at the URL you used today, as well as estormwater.com. So long, everybody.